Thanks for coming out, everybody. I'm really excited. This is I've given this talk a couple times, and this is a modified version of it. But it's something I've been researching over the last couple of years, and I hope you find it as fascinating as I do. But again, thanks for coming tonight. I'm going to be talking about the environmental effects of cloud-based computing, the concept of digital carbon footprints, and tools that we as designers, how many designers are in the audience tonight, by show of hands? All right, I'm just going to call you all designers. I think we almost have quorum. That we can employ for behavior change, because we've got a lot of tools and we're affecting behavior change, so why not do it for a little bit of good? In the last 10 years, we're generating more information than we have in the last 10,000. And we're doing this every 2 days. Now, this is a rather bold statement from Eric Schmidt, but when we pause and look around us and see how this is happening, it's selfies. Now, a few weeks ago, my girlfriend and I, we went to the Treasure Island Music Festival. It was a good time. It was the first time going there. And we just noticed a lot of people staging photo ops all around us. And I mean, like, a lot of people were doing this. Now, it's silly to think that the type of information that we're producing every single day that's overwhelming all the other information that we've created since the dawn of time is just selfies. But what the immediate impact was, it was this. The cellular network was maxed out. I had absolutely no service. Now, what's interesting about this occurrence is that despite living in San Francisco, having a network that is 4G LTE capable, it was getting maxed out by the sheer volume of data that people were sharing from the festival. Now, there was a massive demand on an actually very advanced, very capable, very powerful technology. Now, this occurrence wasn't really limited, of course, to that music festival. That occurrence actually has its roots in something that happened over 200 years ago, the Industrial Revolution. And just as a history lesson, it was a transitional period to a new manufacturing process, right, from 1760 to about 1840. Now, this revolution, similar to the computing revolution, had huge ramifications on how we produce and consume goods. But the effects were, of course, studied by economists and mathematicians and researchers. And there was this one guy, William Stanley Jevons, who was an English economist. Now, Jevons studied what was commonly assumed, that, okay, that improvements in efficiency of burning coal-fired steam engines, would actually decrease the consumption of coal, right? Britain's an island, they don't have a lot of coal, we gotta make engines more efficient, what are you gonna do? Now, with more efficient steam engines, you get more for less. Now, as coal became more efficient to burn, of course, manufacturing power goes up, right? And so with that, as you increase your power, people are like, oh wow, this is awesome. I can burn, less and I get more manufacturing power. It gets really cheap because it comes so abundant. Everybody's using it. So as price drops, what actually happens is that demand goes up, right? Now, because this is happening and everyone's adopting it, this in turn, instead of leading to a decrease in coal in consumption for that energy, you actually increase consumption in coal because everyone's using this really cheap, powerful new engine. Now, this became known as Jevons paradox, right? Now, fast forwarding to the computer revolution of today, and if we just focus on those first three, efficiency, manufacturing power, and price, and we replace manufacturing power with computing power, these are the three guiding principles for Moore's law, right? Now, as of course we all know, Moore's law is, over the course of computing hardware, is that the number of integrated circuits doubles approximately every 2 years, right? So on the left-hand side, around 1900, you have the analytical engine, and on the right-hand side, you've got the Pentium processor. So what happens is that it just becomes really cheap and abundant to make computer chips. Now, this excess computing power, of course, is one of the driving forces behind cloud-based computing, the computing revolution, right? Now, I'm going to give you an example of this. So way back in 1994, 20 years ago, Amazon.com was founded by Jeff Bezos. And initially, they were just selling books, right? So, well, as they expanded into e-commerce, they were building up additional computing infrastructure to account for, the larger amounts of data and these giant spikes in traffic. Now, I like to think of this like larger computing infrastructure as like a mall parking lot, right? You're basically building a massive parking lot for these huge bursts in traffic. And really that pattern kind of looks like this, right? So you have the spike during the holidays, and then for most of the time, it's just a big empty mall parking lot. And everyone's like, why is there a big empty mall parking lot? Now this chart is actually the same chart from traffic from the Australian Open. Now there's a lot of websites out there that have this kind of like cyclical process, but the Australian Open happens once a year, just like Christmas or Kwanzaa, right? So what happens is that you have this big lull, and you have all this excess computing power, and you're not utilizing your infrastructure. It's a big waste of money. So last time I checked, Jeff Bezos is a smart guy, and they kind of realized this. And in 2002, they made use of all their virtual mall parking lot, and they created Amazon Web Services, right? And today it's better known as Amazon EC2 or the Amazon S3 Simple Storage Service. Now, today they command a fifth of the cloud computing market. They host sites such as like Netflix, Yelp, Foursquare, really like, huge amounts of traffic. And of course, they're not really the only player in the game. They were one of the first, but there's a slew of other companies out there that provide the computing power for these cloud services. So what we see today is actually a fundamental shift from computing and IT services to what you buy software in a box to actually more as a service, as an actual commodity or a utility. And in fact, John McCarthy, who was a computer and cognitive scientist who coined the early term artificial intelligence, said, "Computing may someday be organized as a utility, a public utility, just as the phone system is a public utility. The computer utility could become the basis of a new and important industry," right? It's pretty spot on. And of course, that new industry is cloud computing, whereby the abundance and excess of processing power and all of its components are really commoditized. And so now today, we actually pay a monthly fee, just like we do with our water bill or our electricity bill. We have our phone bill, right? But you can pay for IT services, what is it, software, what was the software place down the street? Circuit City, they're out of business. Yeah, exactly. They were put out of business, right, probably by cloud computing. Oh, Dreamforce, that's what I'm thinking of. Salesforce. Yeah, man, that conference, I tell you. Anyway, so you have this large excess amount of computing power, and that really sets us up. We're in the revolution today, and that allows us to share and document on a massive scale. And it's something that we do every day. Right now, you might be tweeting, and you're sharing digital content every day. But collectively, we're generating a massive amount of content. So much so that Facebook and some of the numbers that they release, 350 million photos a day is what they handle. 2.7 billion likes, 2.5 billion status updates a day. And this is done by 800, and I think in September they released this number, 864 million daily active users. And actually 703 million of those daily active users are mobile daily active users, right? It's crazy. Now, what is also estimated is that the increase of average mobile connection speed for smartphones, that's increasing 50% over the next 5 years. Now, what's also increasing is the use of that bandwidth. In 2012, we used 353 megabytes a month for smartphones on average. In 2013, we got up to 529 megabytes on average. And so we can only assume that this trend is going to continue. Now, last year, 2013, mobile data traffic was 18 times the size of the internet in the year 2000. Like, that's just like stupid insane, right? Now, it seems that the more connection we get, the more speed that we get, the more we use, right? It sounds familiar. So just like what was going on at Treasure Island Music Festival, we've been filling up this bandwidth. Now, this phenomenon was actually described by Cyril N. Parkinson in a 1955 essay published in The Economist, and actually became known as Parkinson's Law. And what Parkinson's Law states is that data expands to fill the space available for storage, right? So if I'm going to build a big house, I'm going to fill my house. If I bring my backpack, big backpack to go hiking, I'm going to fill that backpack. The demand upon a resource tends to expand to match the supply of that resource. And so this is actually starting to sound a lot like Jevons paradox from way back in the Industrial Revolution. So if we're creating all of this excess computing power that's doubling every 2 years, and we're consuming this computing power and consuming it in massive amounts of data, where does all this data live, right? Now, I've been working on this, researching this issue over the last couple of years, and one of the side projects that I did was called Carrier Cloud, and basically tested our awareness of data. And so in this particular prototype, I actually had half of the participants, they carried around physical packets of their tweets. I printed out all their tweets, bound them up, and they had to carry it around with them for a week. It's like a journaling exercise. Now the other half, they had to carry around a wallet of their tweets, that little packet of Legos there. And they had to decide on what to spend a limited amount of their daily tweets. So basically you're putting a limit on a seemingly infinite resource. Now as for me, I took all of my photos from Flickr and I printed all 1,566 of them. And I carried them around with me for a week. Now I did this, apart from, it was a really pain in the butt, I tell you, but to just really get an awareness, because that's something that's like always on and always there. Now I don't go to my Flickr account that often now anymore, but it's always there. I can just pull out my phone and then boom, within 30 seconds I've got it. So of course, carrying around 11 pounds of photos in a box, that's not where your data lives. It doesn't live in a cardboard box, right? It lives in the cloud. But what is the cloud? Now, it's something that's seemingly intangible. Well, it's not a cloud at all. The cloud is really data centers, and data centers are really the factories of the computing revolution. Now, these massive buildings hold thousands upon thousands of servers. Now, the construction that you see here is a new data center that was built by Facebook that came online approximately 1.5 years ago in Western North Carolina. It's the size of 3 super Walmarts and requires enough power, let me get this right, to power approximately 10,000 US homes, or 40 megawatts. Now that figure is when it's completely filled and it's at max capacity, but it's not at there yet. Now that electricity in Western North Carolina, 61% of it comes from Duke Energy, it comes from coal. Now moving to the other side of the world, this data center is Microsoft's in Dublin. In Dublin is actually, there's a significant amount of data centers from different operators around the world. Now, early last year, Microsoft announced that it's expanding this $500 million, 300,000 square foot facility, and it's building a second 112,000 square foot facility. Now, the total power available to that is 29 megawatts. And of course, 84%, as of 2012, 84% of Ireland's electricity came from fossil fuels. Now, coming back to the US in Tulsa, Oklahoma, here's HP's 404,000 square foot data center. It's built to withstand, I kid you not, a force 5 tornado, which is about 200 miles an hour. And it's the power supplied by the Public Service Company of Oklahoma. 68% of that power comes from fossil fuels. Now, 14% of it comes from wind energy. And it's under a long-term contract from HP, which is a good thing, right? So nowadays, Facebook actually has 5 dedicated data centers of its own. But it's all brand new construction over the last 4 years. Now they've actually built a 6th data center in Prineville, Oregon, for all you Oregonians out there, that's basically going to be serving nothing more as a giant digital shoebox, right? Like we don't go to our Facebook photos all the time, so that stuff's going to be in cold storage, and that's really the reason for that 6th data center. It's basically going to be handling 240 billion photos that we don't access on a daily basis. So it's actually been estimated that Google actually has 36 data centers worldwide. Now, if that kind of seems like a lot and you think of that scale, it pales in comparison to the nearly 500,000 data centers around the world. Now, some of them, of course not all of them, store our daily interactions. But the majority of these data centers are powered by non-renewable energy resources. And that's really what I've discovered in my research over the years, is that the cloud really is CO2, or carbon dioxide. Because every interaction, every tweet, every Instagram, every like out there contributes to that. Now, in order to summarize this problem space, I just created a little tongue-in-cheek interaction, the coal button, right? It's kind of like lampooning those one-click interactions, like the like button or the Tumblr reblog. Now, I encourage you to go to thecoalbutton.com to learn more about the problem space. And remember, behind every click, there's a little lump of coal. So now that we've identified this problem, right? It's like, okay, identify the problem. Does anybody give a shit, right? It's like, should I pursue this anymore? So what I wanted to do was actually ask the question, does the correlation of digital behavior with carbon dioxide emissions lead to a change or awareness in user behavior around the digital production of content, right? So I created another project using Legos and the service ifthатthenthis's.com, and I created emission bricks, which is basically a physical dashboard that sits next to someone's desk, and it displays the CO2 emissions of a participant's daily interactions. So similar to the Carrier Cloud prototype, it wasn't a digital interface. It's really kind of a step before that in that process. When I'd like to do these more analog explorations, it's really about designing a journey for a participant, and then you get to see where they go, and you just follow them along, and they're like, oh, I didn't know we were going to go here. And then that kind of leads to where you want to go next. So I did this over a 2-week period and updated the dashboard daily and posted the results to Tumblr and to Twitter. Now, a summary for the participant's behavior is on the right-hand side. But one of the many insights that I gathered from doing this experience was the confusion over what a gram of CO2 is, right? What's a gram of carbon dioxide? Because when we talk about CO2, we talk about it in terms of weight in grams or in pounds. And I think that's weird because just like the cloud, CO2 is, it's emitted into the atmosphere. So I'm going to try an experiment with you and get us to think about data in CO2 in terms of volume and space rather than weight. So I actually I didn't have enough to hand out, I only had one, but I brought a test tube that basically it isolates 1 milliliter of space, 1 milliliter of volume, right? It's nothing in it except for air, but it's basically the size of, maybe like half your pinky or like a pen cap. So if we start to think about the volume of that space, let's think about the volume of that space. Okay, cool. Let's get started. So 3 years ago, Rafi Krikorian, who was actually a senior director of engineering at the time here at Twitter, he estimated that the carbon footprint of a tweet at 0.02 grams. Super, super small, right? Now the volume of 0.2 grams is 10 milliliters, right? Or 10 of these test tubes, right? Now, going a little bit bigger, Google actually published the size of the emissions of a Google search at 100 milliliters or 100 test tubes. Now, that's still kind of small, 100 milliliters. Arresting human breath, adult breath, is 500 milliliters, like when you're sleeping. So 5 Google searches, and I just filled your lungs with carbon, that's so morbid, carbon dioxide. But every day, Google handles 3 billion searches. So now if we scale up to, say, an email, a typical email emits 1,250 milliliters, right, or 1.25 liters. It's about the size of, a little bit bigger than an Nalgene bottle. But it's like, hey, Dave, emails are more environmentally friendly than letters, right? You don't have to make the paper, you don't have to deliver it, you don't have to send it, and all that stuff. It's actually about 1/60th the carbon footprint of a letter an email is. But ask yourself, how many letters have you sent in the last year? And how many emails have you sent in the last year, right? Probably not as many letters as you have as emails. Now, this is actually a good example of what's called as the rebound effect. Now, the rebound effect is really a core consequence of Jevons paradox, whereby you have a lower CO2 intensive technology that results in a higher CO2 output. And it's just simply because we just do it more of it, right? So looking at emails and scaling all the way up to data centers in the US, each year, 9.23 quadrillion milliliters, or 10 to the 15th power, of CO2 is emitted into the atmosphere. Now that's more than Argentina or the Netherlands emit during an entire year. So to summarize what we've covered so far, right, we're seemingly bound by a paradox of efficiency, and we're increasing that efficiency with computing power. And which is kind of given birth to this new computing revolution, and through its commoditization, we're filling up that computing power and all the bandwidth with massive amounts of content. Now that content lives in data centers, which of course, are powered by non-renewable energy resources. So what's being done? Well, within the industry, one of the guiding principles is efficiency, right? So server designs. Server designs are open source. You can download CAD drawings of them. They've got racks and fans in there, and their designs are constantly being worked on. Facebook actually has a 3-year-old project now called Open Compute Project, which has improved server efficiency by 38%. And they're actually looking at Facebook, Dropbox, and Amazon. They're looking at solid state drives, actually, which of course have no moving parts, very little cooling, less energy, and they typically have higher data transfer rates, right? So there's a debate on whether or not it can scale up that high, but it's going to come, which is great. There's also advances in cooling systems. Green Revolution cooling, they actually submerge servers into liquid coolant, so they reduce their energy costs by 90 to 95% as far as cooling costs go. Now, the picture you see here is inside a data center, one of Google's data centers in Douglas County, Georgia. So it's kind of like Willy Wonka's chocolate factory here, but the blue pipes are cold water. The red pipes are water returning back to be cooled. And then that bright pink pipe, in this photo, it goes from the row of chillers, which are green, and then to the outside cooling tower where it evaporates and then cools off and brings it back down in. And then, of course, there's improvements on the actual data centers themselves. We've come a long way. So this is that cold storage facility by Facebook in Prineville, Oregon. That's this one right here. It's LEED Gold certified from the U.S. Green Building Council. It requires 52% less energy to operate than a facility comparable to its size, right? Now, Facebook's committed to reaching 25% renewable resources across its data centers by the end of 2015, which is great. So they're making strides there. Now, Google has actually invested over $1 billion in renewable energy projects, which include 2 long-term contracts over 20 years to buy renewable energy from wind farms, which also helps stabilize and decrease the cost of wind power. Now, pictured here is Google's data center in Finland, which uses seawater as a coolant rather than compressor-based or refrigerant-based. And now across all of their data centers, Google uses 50% less electricity than a typical data center. Apple, this is actually where iTunes, when you ask Siri a question in your iCloud, this is where it lives. It's a $1 billion, 500,000 square foot facility in Maiden, North Carolina. And there's a 20 megawatt solar panel array that covers an area of 76 football fields. And there's another one in similar size a couple miles away. Now, these are enough to provide nearly 60% of all the facility's energy needs, these solar panels. Now, this is all great news, right? But these are just a few companies out of the hundreds of companies out there that are providing cloud-based services. Now, that's what's being done on an industry perspective. And I'm glad we're all designers here. I mean, I'm not an engineer, I'm a designer, right? And engineers have tools to make data storage and energy use a lot more efficient, right? But I don't have those tools. I've got other things in my pocket, right? What are the tools that we have that can affect behavior while making a compelling user experience, right? So we have a variety of behavioral concepts at our fingertips that we can bake into our experience to nudge users into certain directions, right? For instance, a test tube is a conceptual metaphor, right? I'm taking a really large kind of concept that's really hard to grasp, and I'm boiling it down into something we can grasp and that we can understand, right? So when we think about, and every designer loves Venn diagrams, I really wanted to take these larger concepts of big data and the environment and really make it compelling to you, the user. So a few years ago, I worked on a project where I took some of these behavioral concepts and kind of baked them into data in the environment. And I created a concept project called Canary. Canary really is it's a conceptual service that allows you to track and offset your digital carbon footprint. So we basically just connect it with the various social networks that you have, and you get to see that feedback of your activity on those various networks. So on a high level, what I want to cover with y'all tonight is 5 basic behavioral concepts. Feedback loops, which we all know and love, normative comparison, appropriate challenges, triggers or nudges, and status. So feedback loops, of course, when it comes to global warming, the length of that feedback loop is generational. It takes a really long time. That's why nobody really believes it, right? I can spray aerosol can and I don't see it. What's the effect? I don't see it. My grandkids will see it. So what a unique proposition with digital interactions is that we can shorten the length of that feedback loop to about a week. So it's like, oh, okay, I hooked this Instagram up to Canary. I can see how many photos that I've taken in a week, all right? I have a concept of how much I'm actually, what I'm actually making. But as we all know, pretty mirrors get boring pretty quickly when it comes to user behavior. So instead of looking at your own production, you can compare yourself with others. And that gets us to our second behavioral concept, which is normative comparison. Now, normative comparison states that above all other factors, we compare the status of others to ourselves, and we want to normalize their behavior to that. So if we, put your friend Carly and we compare ourselves to Carly, we can actually see that we've taken 5 less photos. So it's like, all right, we're not taking as many photos or selfies as Carly. All right, I know what's going on. Right? Now, another possible feature for this service is an appropriate challenge. So what you can do is you can say, all right, well, I'm going to set myself a goal. I'm going to say, you know what? I'm going to try to make even less. So I'm going to set my goal down to 14. So I'll take less photos. So I won't produce as much content. So an appropriate challenge really is a challenge that strikes a balance between something that's really overwhelming and something that's really boring, that's achievable. And you leave it up to the user to do that. But the thing is, you're not going to constantly go back to that app to check that new app that you've downloaded, right? You want to basically interrupt that path where that user goes, maybe on Instagram or another app where they're already, producing that content. So go beyond the application and kind of give that nudge or that trigger, which is really just kind of placed along those regular paths of a user, and remind and motivate that user to take action. So if you can't access Instagram's API, there could be a push notification, right? So the fifth and final behavioral concept is status, or sharing your status. So in Canary, it's like, okay, I can offset my digital carbon footprint and donate to a wind farm in Ohio. Well, that makes me feel good, but I want to share this status and share it out there with others to establish what I think is my personal best, and then see how other people react to that and see how other people are doing as well, right? So keeping these concepts in mind, I think as designers, we have a responsibility beyond making experiences that are simply efficient, getting people to come back more, and then constantly saying hey, use me again, use me again. We should really create compelling experiences to help uncover the larger systems at play, especially those which we and all our users depend on every day. We depend on this massive data center infrastructure. And actually, some of these behavioral concepts are being used today in products. Actually, just down the street, Opower, they're a really cool company. And they partner with utilities to redesign those really crappy utility bills to basically show customers how they're performing to their neighbors that are similar to them. So you can see that blue bar in the middle, which is basically, it's like, all right, well, I'm using more power than people that are similar to me, but overall I'm doing okay. Now, since 2008, customers in the US have saved more than $250 million in their energy bills. It actually works, which is really cool. Their entire business model is based on normative comparison. Now, they've partnered with 80 utilities in 6 countries, saving 2 terawatt hours of electricity savings in 2013. Now, 2 terawatt hours is enough energy to power every home in St. Louis and Salt Lake City combined for more than a year. And that's just savings through normative comparison. So I've kind of talked a lot about big concepts and everything like that, and hopefully I've sparked your interest, and there's some really great resources out there. Tubes by Andrew Blum is a really great book on the physical internet. Literally, there's tubes going underwater connecting the internet. It's not all up in the air. It's literally physical wires. Green Monk's also a really great blog, Tom Rafferty. And Data Center Knowledge, if you really want to fall asleep at night, read Data Center Knowledge. But it's a really great resource. And lastly, I want to thank you all for coming tonight. And yeah, we'll open it up to Q&A. Thanks a lot. So basically, it's like, am I satisfied with the cooling technologies that have been done out there to kind of like lower the carbon footprint? Yeah, I think, I don't know if I mentioned, Facebook built a data center 20 miles north of the Arctic Circle. So they're taking this really seriously, and they actually use the air from outside in order to cool their facility. So they're actually, as far as cooling costs go, are a zero carbon footprint facility. Of course, there's other, you have to have, lights on and everything else, but just from a cooling standpoint, there's a lot of really cool efforts that have been made to do that. There's evaporative cooling, the liquid cooling, placing your data center in an area that's really cold. So it's definitely been done, but it's just a matter of it being adopted by the industry as opposed to a few go-getters out there. Sure. Well, so the question was what's the proportion used for cooling as opposed to power the rest of the facility? The industry actually uses a metrics called PUE. I think it's power utility equivalent, and there's basically, it's like all the power coming into a facility, and then there's the power that's gobbled up by the IT. And so the closer you are to 1, if I'm at 1.2, that's really good. So an industry standard is 1.8, right? So if I've got 20 megawatts of power coming in, and I'll do my math right, if I've got, and my IT is only using 12, let's divide that, I think that's 1.2. So that's doing pretty good, right? I'm right on. Yeah. So yeah, so there's industry standards out there to measure that, so it's kind of like you're not comparing apples to oranges. Sure. So what happens to the question was what are those spikes, right, during the holidays? What happens to that server load? Basically, there's a couple different ways of doing it. One, there's the physical infrastructure of having servers, and of course, then you have that dormant computing power, and then you can rent out that computing power. But basically, it's just like electricity. It's trying to share the load across a bunch of different servers. So what happens is if you have that spike in traffic, then it will fire off some parameters, and will offload that load to other data centers or other servers. I mean, Twitter famously had the fail whale, and so it's we had our servers held together with duct tape. But that was one of the reasons where you just have this overload of traffic, and then it just crashes everything. But now we've been able to stabilize that and not have blackouts. But yeah, it does happen. Sure. So did people actually change their behavior seeing this onslaught of data? I think it was, one of the responses was I like seeing the Legos go up and building with Legos, so I'm tweeting more. But one, it had to do with oh, well, there was, I think over half the participants, I had 10 participants do it, it was a visceral reaction of seeing big black Lego boxes stack up. And another one of it too, it had nothing to do with the carbon output. It really was just, wow, I tweet 98 times a week. How does that compare to other people? They only tweet 40 times a week. Wow, I must be tweeting a lot. I'm going to adjust that behavior. And it had nothing to do with the carbon output. But just really giving that feedback loop and just giving that choice and assuming that people won't make that decision on their own given the information, yeah, I don't think it's the right approach. Yes and no. So the question was, okay, if we're going to throttle down use, basically, if a Comcast says, all right, you have to pay more for more bandwidth. Well, I mean, basically, it'll be a tiered system. So if I'm getting the 100 megabytes a month or the 1,000 megabytes a month, the theory is that I'm gonna fill that up. Right. And so what's gonna happen is that just like the long tail of okay, I've got the 1%ers up here with tons of money, and it's gonna slowly decrease over time, just from the cost of that. That will also fill up with data. But actually, that's a really great question. I'd be interested to see if there is a decrease in it. Sure, that's a great question. So instead of just I'm creating content, if I'm just a consumer, and if we actually think about it, not everybody produces content. There's only a small percentage of people that do it, and then there's a larger circle where people actually curate it, and then everybody consumes content, right? I mean, to get nitpicky, it's just okay, well, if I need to pull that off the server, if it's not cached on my phone, so then I need to pull that data down, so then that's firing off their server. So they're not doing as much work. It gets really technical as far as the calls to and from, whether it's server side or if it's client side. But in Google's, in their more recent estimates for Google searches, they don't really say Google searches, it's more of a Google customer, and they actually think about the battery life or the power that goes into, say, like a phone or to a laptop, as opposed to it just being on the server side. So any tracking, or would there be any momentum really behind tracking people's CO2? I think there's really great like microsites out there where it's just like, oh, you know, GE partnered with Pentagram, and then they showed like the, you know, oh, this is, you know, when you turn your light bulb, you know, 100 baby rabbits die or something like that. But like, it's just really informational, where it's just like, oh, I'm showing this, okay, well, what am I supposed to do with it? And that action, that feedback, it's like, okay, well, can I offset it? And can I, you know, do something about it? Can I donate any money? Do I consume less? I think that's the next step. And right now, we're just in that, I've got the information. There's not the tools that we could be making to close that feedback loop. And it's happening with other things, but not with CO2. Oh yeah, totally. So yeah, if businesses were able to include that as part of their performance, is, you know, include that carbon dioxide production. Yeah. I mean, I think that's a great point. It is at odds, but, you know, of course, with like capitalism, it's just like more and more and more, grow. But eventually, you know, you're going to hit this ceiling. And I mean, I don't know. I think right now we're in a really unique time that we're expected. Okay, we got to create a hammer, you know, to drive the nail into the wood. But now you got to try to make the hammer buzz, so then people will pick it up and drive more nails into the wood and keep on using it more and more and more. And it's just like, I think there's a space there and there's an opportunity there that it's open. There's a market opportunity there, for sure. Great question. So the question was basically, it's just like, you know, can we do better than putting solar panels on top of parking lots to power data centers? I think getting more efficiency is great, but it's a zero-sum game, as I've kind of explained. Notwithstanding the cars, which I don't think cars are that great, but that's a whole other thing. But I think locating data centers further north of the Arctic Circle is a really great way to cut down a lot of those extra costs that will raise that PUE, all the ratio that's going into the heating and cooling and the powering of it. Yeah. Oh, totally. So the question was, okay, you're going to locate these data centers in remote parts of the Arctic. How do you actually bring the materials and everything up there? There's actually, if you do just a little bit of research for Google Images, Facebook documented the building of their data center that's 20 miles north of the Arctic Circle, and you can see where they're basically like laying down. It's actually, I mean, they're laying down roads. It's almost like logging roads. So it's like, okay, if anybody's been out to Olympic National Park, there's logging roads, but there's only 3 of them out there, and that's the only way to get stuff in and out. But I mean, Facebook's printing money, so basically they could, yeah, exactly. But they see it as a longer term investment because they know that we're uploading 350 million photos a day. So it's in their best interest to be making these larger bets that may cost a little bit more for long-term growth. Oh, sure. There's a really, so I actually, normative comparison, and like I came across normative comparison when I was doing my research around, and I came across Opower, and I was like, oh, they're basing this off of this business model. There's a really awesome deck. Some of you might have it. Mental notes. And it's just basically a card deck of about 50 or 60 cards, and it's all those behavioral concepts: loss aversion, set completion, priming. There's just a whole bunch of them. But in developing this project, it was just like, okay, given what I'm trying to achieve with the subject matter, it's like, what are the few ones that I can like pick out and pull out? And there was a couple. I skipped over a couple of features that were that had some of those in there, like set completion. But they're really great, and they're awesome. I use them at work. Thanks a lot for coming, and enjoy.